Thank you very much, Yasemin. Thank you all for coming. It is a humbling introduction. I appreciate you coming here, and it was a pleasure to work with Yasemin many years ago. And it's the first time I'm actually wearing this, so I'm not exactly into costumes, but we decided to go all out, and we'll see. So we're gonna see how Halloween and the Big Bang are gonna go together. Maybe we're gonna do it every year. Okay, so let's get to it, and let's talk about ghosts, phantoms, and monsters in the Battle of the Big Bang. So, but we're gonna start with a question. It's a question that may haunt you during these days or any other day, especially as you get older, like I do when your hair starts to grow white. That's the question of what is the oldest thing you can remember? So I wondered about this question. The oldest thing I remember is the outline of a room I cannot recall. I cannot exactly recall which city it was in or when I had that memory from. But I did grow up in the city of Tehran, so chances are that it's a room in that city, but it may be some other city. The oldest thing that Phil remembers is, I don't know if you could, oh, sorry, this is a little bit tough. Do you mind actually turning down the light here? Because I don't think it actually comes out very dark.
Which one is it?
Okay, very good. So this is a proper spooky. In case I just disappear, you should be alarmed. Okay, so so as I said, this is where I grew up, and the oldest memory that Phil had is pretending to be a cat. But this demon you see there, the little demon, is not Phil. It's Phil's cat. And its name is Erebus. And speaking of Erebus, you may recall this cat that always accompanies the witch that appears in Halloween. But the name Erebus is actually comes from the Greek primordial god of darkness. And it's an appropriate name because we are going to talk about the primordial cosmos. So the primordial universe is the focus of our story, as is the conflicts and the monsters that lie in our battle to uncover what happened many years ago. So the question we're trying to answer is our earliest cosmic memories. So the oldest thing that we as species can remember is our earliest cosmic memory, which take us back 14 billion years ago. So here things become fuzzy. So we can collectively try to remember what happened earlier and earlier, because none of us have lived that long. But we can remember history the same way that we can talk about what happened 100 years ago, 500 years ago. We can start talking about things that had happened 1,000 years ago, 1,000,000 years ago, or billions of years ago. And we can say smart things about it, but the memory becomes fuzzy around 14 billion years ago. Trying to recover the memory of this era is the subject of both today's lecture and in our book, Battle of the Big Bang, the new tales of our cosmic origins, that you can now buy from all the booksellers or scan that QR code if you wish to. And along the way, we shall battle ghosts, phantoms, and monsters. These are battles that you will participate in, and me and my colleagues deal with on a daily basis, and they all lurk in the dark universe. So we're going to meet these characters and see how we could either slay them or coexist with them. you want to. But battles are nothing new in science. What do we battle about, though? You can go back to the dawn of modern science. Many trace it back to Galileo. And Simon Marius, who is a contemporary of Galileo, he fought with Galileo on who actually discovered the moons of Jupiter. And of course, you usually learn that Galileo did, but Simon Marius claimed that he did. So famously, Galileo called Marius a poisonous reptile and an enemy of all mankind. The history doesn't tell us what Marius responded, but I can't imagine he was very pleased with that, those words. But moving forward in time, there is another battle which is more relevant to the story of tonight, and that's Albert Einstein versus George Lemaitre. So they fought over whether the universe expands. So famously, Einstein said, and you should pardon my French here, vos calculs sont corrects, mais what physique is abominable. Good, I'm glad. I think when I said this in the US, nobody has fired after. Which if you translate, is your calculations are correct, but your physics, like my French, is abominable. So Einstein didn't like Lemaitre's calculation, even though Lemaitre was actually calculating things in Einstein's theory. Incidentally, if you actually put this in Google Translate, it says your calculations are correct, but your physique is abominable. But that's a different story, which we're not going to talk about today. But why were Lemaitre and Einstein fighting for this? So Einstein initially rejected the expanding universe, but his theory predicted it. So Einstein thought the universe was static, nothing was happening on large scale. Turns out that he was wrong, because his theory of relativity predicted it. And relativity says gravity is a curvature of a space and time. But it turns out that if gravity is a curvature of a space and time, or geometry of a space and time, then a space-time is a dynamical, living, breathing thing. And so it can expand and contract, and it will be very hard to prevent it from expanding or contracting. And that's what Lemaitre pointed out. But Einstein didn't believe him, and at the time, the observations weren't clear what was happening. But shortly after, in 1920, Edwin Hubble used the discovery of brightness-period relationship for variable stars, what you see here. So that discovery was by Henrietta Swan Leavitt, who was a famous astronomer, a Harvard computer, as they were named back then, or known back then, who so discovered a relationship between properties of variable stars and the intrinsic brightness. And Hubble used that to measure distances to distant galaxies. And lo and behold, what he discovered, that the farther a galaxy is from us, the faster it's moving away from us. That means cosmos expands, and Lemaitre was right, Einstein was wrong. So that battle was won by Lemaitre, and we learned that our universe expands. But that was not the end. That was, in fact, the beginning of Battle of the Big Bang. And that's our first battle. So, but let's talk about the Big Bang. What is the Big Bang anyway? So imagine everything, the stars, planets, you packed in a hot, dense primordial soup. Then, boom, expansion begins. And that's an animation depicting that expansion of the Big Bang. Big Bang didn't happen at at a point, despite what you see in animation, but it rather happened everywhere around the same time. The universe grew and cooled, and as you can see in this animation, and these are based on real simulations, the gravity formed galaxies, the stars, and eventually died. So we had a almost homogeneous uniform primordial soup, and over time, structures grew through gravitational instability. So that's the story of the Big Bang. But that didn't have to be like that. In fact, around the same time that we discovered the expansion of the universe, there was a different picture that could have been equally correct. So we saw the expansion of the universe. Maybe universe was much hotter and denser early on, and over time it diluted. That's the Big Bang cosmology. But alternatively, you have a so-called steady-state cosmology, where as the universe is expanding, you create new matter, new galaxies, new particles. And over time, the picture looks more or less the same, even though it's expanding. So as expand, you make new matter that basically replaces the empty places between the other galaxies. So you always have a more or less similar looking universe. So that's a different theory. And it was a very popular theory in the first half of the 20th century. And that was actually the second battle you're going to cover, the battle of a steady state versus the Big Bang. So on the left, you have the famous proponents of a steady state universe, Bondi, Gould, and Hoyle, who are famous astronomers. Fred Hoyle, professor in Cambridge, and Bondi and Gould all have discovered important phenomena in the stars. On the right, you have Lemaitre, who we already met, gamma operation physicist who worked on the possible physics of the Big Bang, and Ryle, who's a radio astronomer, British radio astronomer. And in fact, some researchers recently, including one here at Dias, discovered that this steady state picture was originally studied by Einstein himself, although he didn't actually publish this. But yeah, so the story goes back, or the idea goes back to Einstein, who may look like me, although I'm not sure. Yeah, it's actually not that different. Stick your tongue out. Yeah, okay. I see. I think the mustache, he needs to work on his mustache. Okay, good. So, and that was the astronomic, I guess, our first battle led to our first battle between the Big Bang proponents and the steady state proponents. So, how do we decide who won the battle, who wins the battle? It turns out if Big Bang happened, the distribution of galaxies get denser back in time because the universe is expanding. Back in time, everything was closer together as the galaxies were more closely packed. Later, nowadays, they would be more widely spaced. Also, if you go to earlier times, universe which is denser is hotter. You compress things, they heat up. And a hot universe would glow light. So there is a leftover, there must be a leftover flow of microwaves from the Big Bang. So this was in fact predicted by Gamma. And there were other predictions of the Big Bang model that were not expected in the steady state. So the first chapter, this is one of the earlier chapters of this battle, is between Hoyle, the Cambridge astronomer, who was a theorist, and Ryle, who was a radio astronomer, also in Britain. And they, so Sarah and Ryle claim, based on incomplete data, that the distribution of radio galaxies were getting denser in the past. So he actually backed the Big Bang idea. But there were faults in his analysis that were pointed out by others. So certainly Hoyle was not very happy with that. So this led to heated exchange between Ryle and Hoyle. So Woodrow T. Sullivan, a historian of radio astronomy, said Ryle and Hoyle would go after each other like a mongoose and a cobra. So there you go, that's a mongoose and a cobra, to decide which one is which. Okay, so, but that battle was decided decisively, in fact, when cosmic microwave background was discovered, and that was the afterglow that I mentioned. That was not predicted in a statistic. So, so a hotter, denser universe, as I said, would emit light, like the sun does. Radiation cooled down over time, so cosmic expansion cools down the radiation. So even though it originally was very hot, over time it cooled down. And in fact, in 1964, at Bell Labs, Penzias and Wilson in New Jersey, discovered by this radio telescope a radiation from a uniform cosmic microwave background around 2.7 Kelvin, which is minus 270 degrees Celsius. This is what they call a mild Canadian autumn. Yeah. Did we call it an autumn or winter? A spring. I think we call it spring. Yes. But in fact, if you go back to history, even though they won the Nobel Prize for this discovery, they were not the first to discover cosmic microwave background. So it was discovered by a Canadian, which is where I come from. I also may come from, incidentally. Andrew McKellar, who was in fact at some point the head of the president of the Canadian Astronomical Society. So this is, you see, it is in 1940 here. And he actually measured the temperature of interstellar dust or molecules to be around 2.7 degrees Kelvin, although it wasn't exactly clear what was the reason for that temperature. But that's exactly the same temperature that I showed you in the previous slide. So the Canadian microwave background, so by the way, incidentally, so clearly Canada wins over the US in this one. And the cosmic microwave background, I've been told, should be called Canadian microwave background. Okay, moving on. So the CMB is, oh yeah, so that was the end of a steady state, or so we think. So keep that in mind for a second. So the CMB is almost perfectly uniform. But with increasing contrast, we can see, let's see if I can see this, the tiny temperature variations of 1 part in 100,000. Right, so these are, and that's the smoking gun of the Big Bang. So basically, you see a red band that goes across this, that's not the CMB, that's just the radiation from our galaxy. But all these other fluctuations you see, that is actually a picture of the baby universe. And we could use the properties of these tiny fluctuations, with a few microkelvin, to actually infer what was happening shortly after the Big Bang or around the Big Bang. But what came before the Big Bang? That is the question. The Big Bang is often thought to be the beginning of time. So that's you may what you might have heard in a school or learned in a school. So asking what came before the Big Bang must be meaningless if it was the beginning of time. So this is due to the singularity theorems that were proven by Penrose and Hawking, both very famous scientists and mathematicians. And this proved that there is a point where clocks stop ticking. So they proved that there's a point where clocks stop ticking, and they call this singularity. Singularity is this point where presumably there is no before clock stops ticking. So what are these famous theorems? And these are basically one of the things that make these gentlemen very famous. So the singularity theorems prove that the universe began at the Big Bang if gravity is always attractive. The universe has 3 space dimensions and 1 time dimension that we can measure with rulers and clocks. Time travel into the past is impossible. And Einstein's theory of general relativity describes the evolution of the universe on all scales. Now, there are mathematical basically descriptions of all these 4 assumptions, but these are the assumptions that they make in the mathematical form, and those are used to prove the singularity theory, which means that there's a point at which time stops ticking, right? However, most cosmologists, including Penrose and Hawking themselves, conclude that these assumptions can be violated. And some of them, they claim they must be violated at some point. So what does that mean? So that means that there are really two big bangs. Can you tell what's the difference between this one and this one? Anyone? Singularity, yes. They are actually identical, except that I just wrote the word singularity. So there is no other difference. So there is the Big Bang and there is the Big Bang singularity. Right. Okay, let's see, move on. Going forward or not? Yes, we just keep move. Yeah. It's not moving over there. Okay, so there are really two Big Bangs. There is a hot Big Bang and there is a Big Bang singularity. So the hot Big Bang is is basically this history that I told you about, starting from a hot universe and cooling down over time. The Big Bang singularity, by that point where clocks stop ticking, which is a mathematical prediction, but not a physical thing that we looked at. On this question, we actually did a survey about a year ago in Copenhagen, which we published, the Copenhagen survey on black holes and fundamental physics. That involved 100 or so physicists. There are 12 questions about fundamental physics. And in fact, we've done a more comprehensive version of this survey with 20 as many participants now with American Physical Society. And indeed, we get kind of similar results. And the main thing is that there's basically no consensus on answer to any of these questions, with one exception, and it's almost identical the answer to this question. In your opinion, how should we understand the Big Bang? And 68% of physicists in both of our surveys say that it's a theory that says the universe evolved from a hot, dense state that says nothing about whether there was an absolute beginning of time or not. So less than 18% believe that there was an absolute singularity or there was an absolute beginning of time. So that's the consensus. So whoever tells you that the Big Bang was the beginning of time, you can tell them that 68% of physicists do not agree with that. So what came before the Big Bang? And that is the question we'd like to know the answer to, and it's certainly not a meaningless question. So with that note, let me hand you over to my co-author. He's a science communicator extraordinaire, interviewed many great scientists, including Stephen Hawking and Roger Penrose, who are namesakes of the theorems we heard about. And he just happened to run into me at some point and interview me as well, completely randomly. And now he goes by the new name, the destroyer of the worlds. Okay.
Oh, you probably can't see me, lurking in the dark. But yeah, I did come as Oppenheimer, which is kind of appropriate because who's seen the movie Oppenheimer? Hands up. Quite a lot of you. So not only is he known as the destroyer of worlds, but also in the movie, he hands out a paper that on the very day that World War II breaks out. And that was a paper on singularity theorems, which later Penrose and Hawking built on. But what I want to do is take you to our next battle, the battle of inflation. Because it turns out there's a lot of perils in the world. So there are 4 perils in Chinese mythology, and there are also 4 perils that haunt standard Big Bang cosmology. So we have these things called, well, one of them is called the monopole problem, another one is called the horizon problem, another one, the flatness, the structural problem, and lastly, we have the flatness problem. Now, I'm not going to have time to go into all of these, otherwise we'll be here all day. So what I'm going to do is just mention one of them, the horizon problem. So imagine we're telling a ghost story around the campsite. Of course, the fire warms us up, but it doesn't do so immediately. It takes some time. In fact, if the fire heated you up instantly, that will sort of break the laws of physics. There's always some time it takes for radiation to move. But here's the weird thing. The CMB, remember that picture that we saw before? It has the same temperature everywhere, almost up to about 1 pi. And in 14 billion years, there simply hasn't been enough time for the CMB to come to equal temperature. So how on earth did it become so uniform? This is one of the biggest mysteries in cosmology. And one solution offered is called inflation. So what inflation suggests is that the universe expanded exponentially. A figure you might hear is something like we're double in size in 10 to the minus 37 seconds. So let me think, what is that? That's 10 trillionth of a trillionth of a trillionth of a second. So rather rapid rate of expansion. And in fact, less than 100 of these doublings will solve all 4 of the problems of the Big Bang that we mentioned. So let's just look at the one that we examined, the horizon problem. How would a very rapid period expansion solve this? Well, what happens is that in an inflationary universe, because of this incredibly rapid expansion, the cosmos would be vastly smaller 14 billion years ago than in the standard cosmology. So particles can come to equal temperature because they're traveling a shorter distance. And today, inflation is very mainstream cosmology. A lot of physicists are very impressed with this. Here are the inventors of inflation winning the prestigious Dirac Prize. There's Alan Guth on the left. He was the first to come up with inflation, and then it was later developed by Paul Steinhardt in the middle and Andre Linde on the right. And in fact, just to show you how mainstream inflation is, this is a picture from the European Space Agency. They have a timeline of the universe, and there you can see they've got cosmic inflation just happening after the Big Bang. In fact, most of the expansion happens during this inflationary epoch. But having interviewed all of these guys who invented inflation, they tell me something interesting, that this picture you see is actually wrong. Because inflation, if it happened at all, is actually a pre-Big Bang model. So let me try and justify that, because you probably, if you've heard of it at all, you might have heard it just after the Big Bang, as we saw in that ESA picture. But recall that cosmologists now define the Big Bang as a theory that says the universe evolved from a very hot state. But inflation cools the universe down to as cold as it can be, almost as cold as taking a walk out there tonight in this t-shirt. But what you find is that when inflation ends, this energy has to go somewhere. And it goes into making matter for radiation, and that is the Big Bang. So it's not Big Bang then inflation. No, it's inflation then Big Bang. And if you don't believe me, you can take Alan Guth's word for it, because he said that inflation is a prequel to the conventional Big Bang picture. But that leads us to a rather mind-blowing result, something we call eternal inflation. Because inflation has to end, because obviously the universe isn't going through this incredible expansion now, but it doesn't end everywhere at once. What happens is that like a radioactive decay, it happens with a half-life. So the part that hasn't decayed, that bit of the universe that's still undergoing inflation, that's going to carry on and make more Big Bangs. And this will repeat endlessly. And this is known as eternal inflation, and it's why some cosmologists believe we live in a multiverse. Inflation is the maker of the multiverse. It's a bit like a sort of zombie movie. It's just continually reproducing. Who's seen Game of Thrones? A few of you? Yeah, like a zombie army from Game of Thrones. In fact, there's another zombie reference here, because in some sense, this is actually bringing the steady state back from the dead. So it's sort of like an old zombie movie coming to a modern multiverse near you. So let me try and justify how this brings back the steady state. Well, remember that in a steady state, that theory that Niayesh mentioned, what happened was that the universe was static in the very largest scale. And here in eternal inflation, the universe is also static. But what we're going to do is replace those galaxies, remember those dots represented galaxies, with what are called pocket universes. And when you do that, you get something very, very similar to the steady state. And again, I'm going to quote Alan Guth, the inventor of inflation, who said that eternal inflation will strongly resemble the old steady state model of the universe. So in some sense then, this model that we all thought was dead has come back to life. And in fact, that's ironic because the steady state model was inspired by a horror movie called Dead of Night, which came out in 1948. The inventors of the steady state went to see this movie, and it has a sort of looping structure, so you could watch this movie in any order, and the beginning will look just like the end. In fact, Wikipedia said that this movie, which inspired the steady state, was one of the greatest horror films of all time. But one difference between steady state and eternal inflation might be whether this could be eternal into the past. Because it turns out that in inflation, gravity is actually repulsive. That's what's driving this exponential expansion. And this actually violates the singularity theory. Do you remember those 4 assumptions that was made to make sure that the Big Bang was the beginning of time? One of them, that gravity is always attractive, but inflation has this repulsive gravity. So it violates the singularity theorem. But that doesn't mean inflation can be eternal into the past. People have studied this. And one group says actually inflation cannot be eternal into the past. It's only eternal into the future. So it will make many, many, many universes, but it must have had a starting point. So that was a study from Border, Guth, and Vilenkin. However, more recently, another study from Lesnevsky, Essen, and Davis. So actually, inflation can be eternal into the past. So the universe, in this sense, was never, ever born. It's always existed. There's another study also on this, came out very recently by Gesnajani, Ling, and Quintin, and they were like, oh, maybe it can. Maybe it's inflation can be eternal. In fact, I should say that the lead author on that last study is none other than Niayesh's wife, Gazal. But, so it's not clear whether inflation needs its own prequel, but it is a prequel to the Big Bang. However, not everyone likes prequels. Yeah, so not only the Phantom Menace, but I've also told that the prequel to The Exorcist is a particularly bad film. So definitely don't watch that one. So there has been this sort of rebellion against inflation recently. And leading the rebellion is none other than Paul Steinhardt, you see in the middle. You might remember him as one of the creators of inflation, but he sort of turned against it, publishing articles in the literature and in popular science magazines. So there's been a lot of controversy there. He is with his colleagues Anna Eas and R.V. Loeb. So I went to interview them and said, well, what's your beef? Why do you not like inflation anymore? So one criticism is that there are too many models of inflation. So there's actually lots of different ways that the universe can inflate, and there are so many models I couldn't fit them all on the screen. And that leads us to question the claim that inflationary cosmologists will make. They say, oh, we plotted out all the details of the cosmic microwave background, and inflation fits the data perfectly. And the critics will say, okay, which one of these models fits the data perfectly? So that's one criticism, but I think the biggest criticism is the multiverse. Some people love it, some people hate it. In fact, there was a paper in Nature saying it threatened the integrity of physics. I went to interview R.V. Loeb, who is one of the critics, and he talked about the multiverse and said, what did he say? He compared the multiverse to taking recreational drugs. You will feel good. I'm sure Alan Guth feels really good about the idea of the multiverse. Doing physics is not about feeling good. Now, one thing I should say about R.V. is that he is no stranger to controversy, because recently he suggested that interstellar comets are actually alien spacecraft. So I'm not quite sure who's taking the drugs here. You decide. But this allegation that the multiverse leads to sort of loss of empiricism, Alan Guth didn't take well to that. When I asked him about it, he said, to assert that I claim that science needs to abandon the concept of empirical testability is a blatant lie. So there's a bit of tension between these two camps. I did actually manage to host a debate between Alan Guth and one of the critics of inflation, George Penrose. That was a lot of fun. But of course, we don't think this is going to be settled by a YouTube debate. What we want to do is find the smoking gun of inflation, or at least what inflationary cosmologists want to do, Let's find out. Is there such a thing? Well, it turns out there may well be. There's these things that go under this weird name called beam modes, and they look like this. What is this? Well, inflation produces ripples in the fabric of space-time. These are known as gravitational waves. And they would imprint on the cosmic microwave background as this swirling pattern called beams. And detecting them is thought to be our smoking gun. And you might have seen headlines a few years ago, just over 10 years ago, of the discovery of beam modes. It made the news. You can see all these different headlines. It was a really big story. Talk of a Nobel Prize for Alan Guth and Andre Linde. I did ask Paul Steinhardt if he'd accept a Nobel Prize for inflation, and he said no, he would give it back. But the Nobel Prize Committee didn't have to worry about that, because it turned out that this discovery turned to dust, both metaphorically and literally. Turns out there's a lot of dust in interstellar space. Here's a picture I took of the Wizard Nebula from my back garden in London. You can see these dark patches are dust lanes. And actually detecting the dust was all the BICEP team actually did. So dreams of a Nobel Prize all down the toilet. And that has led some to say, come on, let's look for an alternative to inflation. So one idea is a cyclic universe. So this would be a universe that would die and come back to life, as it were. Again, a bit like a zombie. So there are different versions of cyclic universes. One is that the conventional one, it contracts and expands, and you just repeat this. Another version is called conformal cyclic cosmology, and another called phantom bounces. A quick brief tour of what these are. So the conventional cyclic universe has the universe expand and contract. And it's said that this could actually mimic inflation. So maybe we don't need inflation if we have this. But the problem is, to bounce, that we need a new field. And these fields, well, in some versions we need a new field. And these fields are called, what are they called? Let's see, our animation. Expand and contract. What could drive this? A new field. It's called a ghost field, believe it or not. So what is a ghost? Well, the idea is that gravity would actually prevent the universe reversing a collapse, because that's what you have to do. You have to collapse and then reverse out, bounce back out. But these new ghost fields can rescue the bouncing cosmology. And how they, well, what happens is normal fields, they gain energy when they move. But the ghost field loses energy. And that can help us give the cosmos an outward jolt and give us this contraction and expansion. So ghosts come to the rescue. And these ghost fields, well, there are two types of ghosts. You've probably seen a few ghost movies. There's the bad ghosts, and these called wild instabilities. Very much like the Slimer from Ghostbusters. Anyone seen Ghostbusters? None of you have seen Ghostbusters?
A few that I can
Okay, good.
I don't want to confess that.
Okay, yeah, something you might not want to see. And there are also good ghosts, Casper the friendly ghost here, and they would allow for turnaround without these wild instabilities. So the cyclic proponents are looking for these good ghosts. Another alternative is called conformal cyclic cosmology. That comes from Sir Roger Penrose, who was one of the authors of the standard Big Bang singularity. And this needs no ghosts. So what Roger Penrose suggests is that if mass becomes irrelevant, then the universe would lose its sense of scale. And then you would have a transformation. Big and small would become equivalent. The far future could be mapped into the beginning. You'd have infinite eons without any bounces. Another alternative to inflation is that these monsters that live in the center of galaxies are giant black holes. They could give birth to new universes. These are known as black hole genesis models. Some of these ideas include inflation. Some of them seek to replace inflation. In fact, Niayesh managed to create one which made the front cover of Scientific American, and that does not require inflation. So another cyclic universe is called a phantom bounce. So what is dark energy? This is the key question that the phantom bounce addresses. And the idea that most people have is that it's a constant energy for the vacuum. So think of empty space just having some energy in it. And this is an empirical discovery in 1998. But the question is, could it change with time? And there are some theories in this room that suggest that it could. And in some versions of this change in dark energy, you actually get what's called a phantom field. And so what this would have, this would give us what's called the big rip. So this means that dark energy would go to infinite value in a finite amount of time. And it would literally rip the universe would expand so fast, that it would rip every atom in this room to pieces. Everything would be destroyed by this phantom. But some people have suggested that a new universe could be born from the fragments. So again, we would get a sort of cyclic universe, but it wouldn't recollapse like in the traditional cyclic universe. One last alternative to inflation is known as variable speed of light theory. And here the idea is that it wasn't the expansion rate that was really fast in the Big Bang, rather it was the speed of light. And that could also solve that horizon problem because communication would be very, very easy if the speed of light is very, very fast. And Niayesh, again, has worked on variable speed of light theory. But if inflation did happen, and it did have a beginning, we could still ask what came before. And one idea comes from the cosmologist Alex Lenkin. Here he is, when I went to interview him. And he's asked us to think about quantum mechanics, this physics of the very, very small. And what that suggests is that particles can fluctuate from the vacuum. So he said, well, what if space could be treated quantum mechanically? But then it should fluctuate into existence from a state where there was literally no space. But how could you actually realize that? Is this really what happened at the Big Bang? What we think we need is a really deeper theory, a new theory, theory of quantum gravity. And for that, I'm going to pass back to my colleague.
Very good, thank you. That brings us to our next battle. It's the battle that my character also was very much involved with, as am I, and that's the battle of quantum gravity. And if you haven't heard about this, that's the holy grail of theoretical physics. And that's basically trying to answer this question: can the rules of quantum and gravity work together? So we have the rules of quantum that govern the subatomic worlds, your cell phones, everything electronic, the Zoom that uses to broadcasting outside this room, that uses the rules of quantum mechanics, but also we have rules of gravity that black holes are governed by, and the GPS that we use to locate where we are, it uses general relativity of rules of gravity. Can these rules work together? They're both very successful. But it turns out that there's a catch. And the way I can explain it to you is what I like to call a Heisenberg versus Einstein microscope. So there are kind of two kind of microscopes you could make based on the rules of quantum mechanics and relativity. So in a Heisenberg microscope, you need higher energy to see a smaller thing. So higher energy leads to shorter wavelength, that means better resolution. This is why you use X-ray microscopes to see very small things, or electron microscopes that are even higher energies. So you just need higher and higher energy to see a smaller and smaller things. But in the opposite case, if you use rules of general relativity, higher energy leads to bigger black holes. So black holes have a lot of energy, they're very massive, and the more energy, the more mass you have, because E equals mc squared, and the bigger they get. So actually that gives you worse resolution. So there is actually a conflict between these two, and that's basically the essence of why quantum mechanics and gravity are not really consistent with each other. And incidentally, if you wonder who this gentleman is, if I when last time I Googled Heisenberg, this is the most common picture that I found. There is an older one, and you guys, if you haven't done this, you could try Googling Heisenberg. And incidentally, this is not the last scientist who was accused of dealing drugs. If you actually watch the TV series that this character is based on, Breaking Bad, we should say. Breaking Bad, yes, you can Google Breaking Bad and find it. I've been told it's a good TV. But if you read our book, we have a story of another cosmologist who's been accused of being in charge, but of course he has denied. But let's get back to the story of quantum gravity. So what is actually happening if we try to unite quantum mechanics and gravity? And it turns out that there is a zoo of possibilities. Some of them people in this building actually work on causal sets. Yasserman and Benjo, they are actually, Benjo, can you see that? They are pioneers and people who are actually working on this. But there are many other possibilities. String theory is very popular. I'm going to talk about that in a minute. Loop quantum gravity, a lot of my colleagues work on it, but there are others possibilities. This idea of Ojava ellipsis gravity is something I worked on related to faster than the speed of light that Phil mentioned, but there are other ideas. Universe could be a fractal and all sorts of things. So these are all ideas and speculations about what is the fundamental nature of a space-time. A string theory, which is the most popular one, many physicists work on it, says that you should replace point particles with a string. So you don't really have particles in nature. Quantum theory of gravity should have strings instead of particles. And that gives finite answers. And gravity emerges from particle physics in its description. However, there is a catch. You need 6 extra dimensions to actually make the mathematics work to get finite answers. And you also need a new symmetry called supersymmetry, which unites 2 different types of particles, fermions and bosons, with each other. And lo and behold, we haven't seen any of this. We haven't seen these 6 extra dimensions, and we haven't seen supersymmetry. We've looked for it, and we haven't found any of them. That doesn't mean that it's not there. It might be just beyond our experimental approach, but that's not. That's very disappointing. On the other hand, maybe the next popular proposal is so-called loop quantum gravity. They carry the idea that the space is discrete and can't be divided into even smaller pieces. So there's basically fundamental quantum of the space. It cannot be infinitely compressed, so there is no singularity. There is no need for extra dimensions or supersymmetry in this theory. However, it has its own caveats. For example, cannot explain other forces of nature other than gravity. And here is a movie. Let's see whether it works.
You agree with me, right? Loop quantum.
Okay, so we should increase the volume. Let's see. Oh, yeah. Okay, so let's see. You have to.
You agree with me, right? Loop quantum gravity is the future of physics.
Sorry, Leslie, I guess I prefer my space stringy, not loopy.
Well, I'm glad I found out the truth about you before this went any further.
Truth? What truth? We're talking about untested hypotheses. It's no big deal.
Oh, it isn't really? Tell me, Leonard, how will we raise the children?
I guess we wait until they're old enough and let them choose their own theory.
We can't let them choose, Leonard. They're children.
And that brings us, sorry, the quality of sound was not terribly good, but the real question is that you cannot test these theories, but we need to really know the answer because otherwise we cannot raise the children problem. So, which is, we're going to come back to that existential problem in a little bit. But incidentally, Phil also hosted a debate between one of the pioneers of loop quantum gravity, Carlo Rovelli, who's actually also a well-known scientist and science communicator, and David Gross, one of the pioneers of the string theory. And you could also watch it for yourself and see who actually won the debate. But again, it's not who wins the debate that decides this, it's observations. So, so there are many ideas in a string cosmology. So let's just speaking of how this quantum gravity relates to cosmology. There could be these extra dimensions, there are membranes that collide in these extra dimensions. There could be gases of strings that you see here that form in the early universe. There could be holographic cosmology, basically ideas that basically dimensions are vanishing. Maybe dimension of time vanishes as you go to early times. And I worked on, for example, that last one. This is from one of the pioneers, one of the fathers of a string theory that believes there was a pre-Big Bang. Basically, believes that the beginning of time is a myth, and which is in agreement with many of the proposals we discussed already, or Phil discussed already, that in fact string theory predicts some kind of a bounce. That was his idea. Not all the string theories that we know. On the other side, loop quantum gravity also predicts some kind of a bounce. So these are the proponents of, or the fathers of loop quantum gravity. Niayesh Afshordi, who's my colleague, Abe Ashtekar, and Carlo Rovelli. In particular, Abe Ashtekar has been suggesting that singularity is replaced by a big bounce. He has his program of loop quantum cosmology. So he thinks it leads to a bounce, but then another loop quantum gravity researcher, Martin Bojewald, disagrees. So, so the jury is still out, but the idea is that they could, based on quantum cosmology, loop quantum gravity, get a bounce without a ghost, which is a good thing because we didn't like ghosts. There is another idea that was put forward by Hazal, who was introduced earlier, and she has introduced another beast, another kind of a monster called Kaskutan, and that actually leads to a scenario which also has no singularity and no stability and no ghosts. So that's another way of getting bounced. But in this case, you have to have a speed much faster than a speed of light, infinitely faster speed of propagation. So to wrap up this part of the battle, so this part of the battle is not really finished, and it's an ongoing battle, like many others. But all these approaches, what they have in common, that Big Bang was not the beginning. So 14 billion years ago is only a lower limit on cosmic age. And that brings us to our fourth battle of science and religion, which on other words, how do we read the children? Okay.
Thank you. So this issue whether the universe had a beginning is interesting to philosophers as well as physicists, and I think everyone will be fascinated by this. And in fact, it's been suggested that if the universe did have a beginning, could this prove the existence of God? Now, you might think that Georges Lemaitre, being the father of the Big Bang and also a Catholic priest, would say the answer to this is yes. But in fact, he said no. He thought we should separate our science and religion, keep them completely separate. However, there are philosophers out there, this one, William Lane Craig, American philosopher and theologian, says yes, that actually the Big Bang would prove the existence of God. And he has this argument, it's called the Kalam cosmological argument. It goes like this: everything that begins to exist as a cause, the universe began to exist, therefore the universe has a cause, and he's got various arguments that must be God. But and what he does is uses the Big Bang as evidence for premise 2 of this argument. But I think what we've shown is that we don't know if the Big Bang was the beginning or not. Might have been, might not have been. So we can't really secure premise 2. And in fact, even premise 3, even premise 1, people don't know if causality is fundamental. Some people think it's not present in the fundamental laws of physics. So I don't think we should buy this argument. But that doesn't mean there couldn't be some kind of creator. And it has been suggested that we might be able to make a universe in a lab. It would require some fantastically advanced civilization. But Fari, Guth, and Gudin studied this. And what they found is if you could make like an inflationary universe, what would happen is it would appear to you as like a mini black hole, and it would pinch off from your space. So it wouldn't invade your space. You wouldn't even know it was there. So that means you could not hear any prayers from the people you created. You couldn't communicate with them and give them moral commands. And there'd be no reason to think that the creator of this universe would be a perfect being. I've spent a bit of time with Alan Guth, and he's a very charming, lovely guy, obviously incredibly smart. But he did, in fact, win an award for having the messiest office in Boston. But if you were to create a universe, would you sign your creation? You know, like an artist puts their initials in their painting. Can anyone see any initials in here? Could you see the name of the author of creation? I think I do. Maybe I'm going to help you out here. I think I see SH. So perhaps the creator of the universe is none other than Stephen Hawking, who traveled backwards in time to create the universe. In fact, there are, believe it or not, there are models of the early universe which allow for time travel into the past. So there's two versions. One has a little time loop at the origin of eternal inflation. That's called the Godin model. You see that on the right. And this one on the left, the entire universe is a time loop. Something a bit like the movie Groundhog Day, but at a universe scale. And in fact, Niayesh is one of the creators of this model. But of course, this is speculative. Let's be honest, it's quite speculative stuff. I mean, is it really science? So the question is, how do we tell the difference between pseudoscience and science? Well, I don't think that there's an exact demarcation criteria. In fact, philosophers do not like the idea there's a single demarcation between science and non-science. But there's, I think, a good summary coming from Richard Feynman, who also appears in the movie Oppenheimer, the chap playing the bongos. And he said that the game I play is a very interesting one. It's imagination in a tight straitjacket. So that straitjacket is made of data. So as we get new data, we tighten Feynman's straitjacket, and that reduces the room for theorists to run wild with their imaginations. And the idea is, as we get new data, we can maybe reveal a winner in the battle of the Big Bang. And how we could do that with new observations, I'm going to hand over to Niayesh to finish us off with the final battle.
Thank you. I know we've got a little bit over time, but this is, I promise you, this is the end. This is the final battle. So we're going to decide who's going to win, hopefully soon, next -2 minutes. But unfortunately, NASA decided to cancel a lot of the missions thanks to Trump's 2026 budget. So it may take a bit longer to actually find out who wins the battle. So all of these missions that were designed to unravel the origins of our universe might lose their funding. But if that doesn't happen, we can try to look back in time. And one idea, one basically secret weapon that we have is that even though around 380,000 years after the Big Bang, we see the CMB, it is actually kind of like a wall because the universe becomes very dense and opaque at this point. So you cannot really see behind the CMB because the universe is dense and opaque. But like ghosts that can pass through walls, we have a ghostly being that could actually walk through the walls. And that ghostly being is the gravitational waves that we talked about, the fluctuations, ripples in the fabric of space-time that are generated in some Big Bang models. The ripples in the fabric of a space-time has been detected, but it hasn't been detected from the Big Bang, despite what Weiss's originally claimed. But it has been detected from colliding black holes. So this is this LIGO detector that you see here through laser technology. But these, if they are generated at the Big Bang, they can travel through the CMB like a ghost can travel through the light, through the wall. And some models, like some inflationary models, predict it, while others do not predict a lot. So by detecting these gravitational waves, or even not looking for them and not finding them, we can rule out or prove some of the models, at least verify some of them. So we could look for B modes again. So this is an example. Simon's Observatory in Chile is going after this. Or we could try to directly detect this. You could actually first look for B modes in a space, go out in a space. And this is Lightbird satellite by Japanese Space Agency that has been proposed. Or you could directly detect it via something like a Big Bang observer, which is a super LIGO in a space. So there's a prequel to this known as LISA, which is yet to fly. But if that works, then the next target will be Big Bang observer that hopefully will detect Big Bang gravitational waves directly, if they are there. So that's it. The final battle is yet to be decided. But I hope what you take away from this talk is that the real monsters and demons that we talked about and referred to, they do not walk among us, despite all the fairy tales we tell our kids to scare them. The true demons lurk in our ignorance. Our quest is to comprehend the cosmos, ourselves included. That's the way we could overcome our demons. And in this process, our silver bullet is the scientific method. So what Carl Sagan called a candle in the dark to illuminate the demon-haunted world. That's the name of his book. So demon being the misinformation, the superstition that kind of governs our lives, has governed it for centuries and millennia. So this silver bullet, the scientific method, will be our ultimate survival tool in an ever-changing world. So the power to remember our past lies in the future. Thank you.